Okay, welcome this evening. Tonight's presentation will be access and use of scientific research data. This was something I came across many years ago, back when Helen was doing her SOFIA trips. And I wanted to access the data that they were getting from the SOFIA missions. And I found the appropriate place for public access to it right up until I explained to them that I could gain access to the data. And then they cut it back and you have to have a user login and password. And several years later, they changed it to, I think it's after 1 year after the data has been gathered, then they provide it for public access and they don't require username and password, just anybody can get it. So it's been a trend, a changing trend within the scientific community that if you make the data, which people paid tax money to obtain and create, that you make it accessible to the general public and maybe they can do something with it. And even this week in the news media, there was somebody doing something with it. So we'll get into a bit of that. But first, as always, let's see, we'll start with the news. And the James Webb Space Telescope, it is aligning its mirrors. The 18 hexagonal segments, they were all what is known as in their launch position. When they were launched, the mirror essentially had knobs. I think it's 4 knobs on the bottom of each mirror segment, and they were retracted by servos and engaged receivers in the back of the primary mirror assembly, so that the mirror segments couldn't bounce around and flop around during the vibration of launch. And so what they're having to do is individually move each one of the mirror segments out so it's free to adjust and no longer held captive by its little probes during launch. And if you think about how small an adjustment they have to make to precisely align all those mirrors, it's at the nanometer level, 10 billionths of a meter, so 10 nanometers per adjustment in the 4 directions. And the first thing you needed to do was move all of the mirrors away from the back by 12.5 millimeters. And if you think about, like, I need to move it 12 millimeters, which doesn't sound like very much, but you're moving it at 10 nanometers per movement. And in order to keep the heat down, you cannot move it continuously through the 12 millimeters. You have to move it a little for that mirror, stop and go move some other mirror, because the servos would build up heat that could be detected. So in order to let things continuously cool down, you have to sort of create this pattern of which mirrors you're moving and how far out you're moving them before you give them a break and let them cool down again. So that's why it takes a month to get all the mirrors in alignment. And I found out that the secondary mirror actually has 6 servos on it. So for those people that were thinking you don't want anything hot out in front of the primary mirror because it would distort the image, the first thing they have to do is move it 12.5 millimeters out from the plane where the secondary is attached, and then they can adjust it. But just like all the other mirror segments, since it's right in front of the primary, they have to move it a little and then wait for it to cool down, and then move it a little more and wait for it to cool down. This is why it takes a month to do this, and why, how come we can't get any pictures yet? I'm sure that the very first pictures would be so blurry and out of focus and have distortions in them, because what they're doing right now is taking their time to get them all out, get them all centered, get all the light pointing in the right place, and then they can worry about focusing them. And there is the primary mirror, there is a secondary mirror, and then at the Cassegrain hole, there is a tertiary mirror. And the tertiary mirror in this mode is fixed. They don't move it. So they're presuming it's in the right place. So now they have to adjust all the primary hexagonal segments and the secondary to get it all focused onto that very small tertiary. And then they can start, moving towards first light. And the first light they're going to get is going to be, if you think back to the early Hubble shots when they were out of focus, That's what the early Webb shots are going to be, which is why they're not going to show them to the general public. Now, as somebody that's aware of certain websites where they store the archival data, I might go grab one as soon as I find out that it's that far along, just to see it. Give it about a month. Now, a little over a month from now, they're going to be doing their rocket burn to get them into their halo insertion orbit for Lagrange point 2, or orbit around Lagrange point 2. So once that's done, they'll have to adjust things again, because the rocket propulsion, now that the mirrors are all unlocked, is apt to vibrate the mirrors. So they're going to have to go back and kind of tweak it some more, even after they get into the halo orbit. And I was looking into the halo orbit, and halo orbit is not just a simple ellipse. If you think of a flat shape that is elliptical, and then you put a bend through the center of it, so it's kind of a curved ellipse. That's what the orbit's actually going to be, is this sort of curved, distorted ellipse. And then it's tilted so that the top of the ellipse is facing away from Earth. And also it's upshifted just slightly above the plane of the solar system. So it's a very complicated orbit that you would think would take lots of maneuvering in order to stay in that orbit. But it's using the light pressure from the sun to push it around half the orbit, and the other one it coasts on. So it's a complicated orbit.
Cool.
Okay, and as they apt to say, astronomers capture the sharpest image ever of the heart of the Milky Way, and what they're really capturing is a handful of stars that are very rapidly orbiting Sagittarius A star, which is the black hole at the center of the Milky Way galaxy. And the way they can do this is they have 4 very large reflector telescopes in Chile and South America, and they're called the VLT, the Very Large Telescope. And they have an optical interferometer that merges all 4 images into one. And they also do the laser-based anti-atmospheric distortion correction of the mirror system. So they can take really sharply focused images of a handful of orangish glowing blobs. But these are the sharpest images ever of the center of the Milky Way galaxy. And they are even sharper than the ones at Keck by about 20 times, they say. 20-fold improvement in sharpness over previous interferometry optical images. And all I can say is somebody in the background over in Germany in Garchings was saying, "Take that, Keck." If you remember, Andrea Ghez actually won a Nobel Prize for the imaging work she did over a 20-year period as part of a team of this handful of stars. And just to drive home the point about how sharp the image is now, they found one more star in this collection of stars. So yes, the sharpest image ever of the center of the Milky Way galaxy. And it just looks like a bunch of orangish glowing blobs. But I get it. It's for scientific research. Now, if they can do this periodically, they can actually calculate the orbits of the stars and more precisely identify not only where the black hole is, but the actual mass of the black hole based upon the orbits. So it's science. And more in the realm of science, they've often, well, when they first started finding black holes at the centers of galaxies, they referred to them as supermassive black holes. Because in order to affect that many stars, that much mass, it had to be a ginormous black hole. It can't be just a black hole. It's got to be a supermassive black hole. So they thought that all large galaxies would have a supermassive black hole at their center. And what they recently found out was even small galaxies, dwarf galaxies, can have supermassive black holes at the core of them. The problem is this black hole is only about 200,000 solar masses. So calling that a supermassive black hole is kind of overstating it quite a bit. But what it means is that if they get more evidentiary data of small galaxies all having black holes at the centers of them, it will give you a closer tie-in to which came first, the black hole or the galaxy.
Yeah, chicken or the egg.
Yeah. So the galaxy is called Mark 462 or MRK. It's Mark Heron, I'm sure. Mark 462. And they have a picture of it. But it's in X-ray. So it's not a true color picture. It's a false color picture. And here was the one that I was telling you about, a citizen scientist. If you're familiar with it, they did launch a couple of years ago a satellite that looks for extrasolar planets or exoplanets using the transit method. And this spacecraft, not manned, it's unmanned, it's autonomous. It's called TESS, T-E-S-S, Transiting Exoplanet Scientific Survey or something like that. But it's kind of the successor to the Kepler mission. And that data is available. And if you sign up to have access to the data, you can become a member of a loosely coupled team of amateur scientists, amateur astronomers, citizen scientists. They go off and look at this data. And what was promising was they came up with a new piece of software called, where is it here? Called LC Tools. And LC Tools is one of these blink comparator software algorithms. So if you have a bunch of stored data that's available on an internet site where you can define how to do a web access to it through like writing some Python code or something, you can go out there and have access to this data, and then you can pick up a picture and then find out where all the things are, and then pick up another picture and find out where all the things are and see if the brightness of a star changed. And what they found out was the brightness of this particular star that Tess had found some exoplanets around it. They found another exoplanet around this star due to a brightness change of less than 1%.
Wow.
And it was less than 1% over a 24-hour period. So this was a Jupiter-sized planet that was transiting sort of a sun-sized star in 24 hours. That means it was hauling around orbit around this star. Its orbital distance is about a little more than that of Venus. So for a planet that's the size of Jupiter to be orbiting its parent star as if it were Venus, I think there's got to be a slide effect going on the gaseous atmosphere where, you know, it's going around so fast that the atmosphere kind of teardrops towards the back. But that's what citizen scientists can find now just by having access to data. And, you know, you do have to learn what the data looks like and how to analyze it. You might, you know, have to go find or custom write some scripting in order to do it. But the data is out there, so to speak, and it's up to individuals to decide, do they have what it takes to go take a look at it? And sometimes like this, it's not really the pictures of exoplanets, it's the brightness curves of stars, and you're looking for a little dip over a period of time. And you use software to find that because you'd go crazy trying to watch all those little curves over periods of time. You're looking for something to go, Yeah, use software to do that. You got recognized as being a member of the team. And I found this one interesting, that there is a project out there called DESI. It's a dark energy survey project. And what they're doing is they gather image data over a recurring basis, and then they measure the microscopic amount of movement or expansion of the individual galaxies, and then they animate that. The project was to do this sort of study for the whole of the night sky, and they've done 10% of it. But that doesn't mean they can't release a pretty picture that's animated. If you look at this picture, it's got little speckles in it, and you can
Yeah.
actually see, like, it looks like ants moving around on a surface from a distance. And then they colored them based upon sort of their distance from the observing point. So you see the further away ones that are red shifted. Now, you can't actually measure directly dark energy, but if you throw a little dark energy in the name of your project, you're more likely to get funding for it, and you're more likely to get your 10% of your total findings to be pushed out there by the media. And keywords like dark energy. Great to see that they're doing something with the money that they're given. But I'll wait until they get the rest of it done.
So this is basically not the real movement, but the extrapolated movement that the galaxies have looking at the spectroscopy. So that's the change, like if it's going to red or to blue, if it's moving far away, or if it's moving closer. So it's spectroscopic, not actually a real movement, but an extrapolated movement.
Yes, and the animation that they were showing is also exaggerated, because if they actually gave you the difference in them, you'd have to watch it for hours to notice that anything changed, and your brain wouldn't work that way. So they exaggerate the deltas, the changes, so that you can visually look at it and see change. But yes, it is spectroscopic data. And if you think that other commercial organizations are launching big satellites into space that's polluting, the visible night sky, or increasing the odds of things colliding, let me invite you to NASA's upcoming launch of their NOAA GOES satellite for doing weather observation. This is a geostationary geosynchronous satellite that is quite a bit of tonnage and quite a bit of acreage of solar panels and radio antennas and cameras. And yeah, this thing is, it's going to be launched by an Atlas V, because you need that much horsepower to launch this one satellite. But it's called GOES-T, and it's going to be launched on Monday from Cape Canaveral using Atlas, one of the last remaining Atlas V's. They've all been spoken for. So there's another satellite we can look forward to seeing in our night sky as it gets to be evening, as it gets to be morning. As the sunlight goes over the edge of the Earth, it will bounce off of the large amount of surface area that this thing is doing. So you can go to heavens above and see GOES-T. And as another example of a busy January for launches, Starlink is going to launch another batch of satellites. And this is once again using the what they refer to as the dogleg launch trajectory. They found that the first stages take too much of a beating on board the ships when they try and return them. Not the actual landing, but once they strap them down onto the flat deck, the ship itself tosses and turns so much that the empty launch vehicle tends to want to slide around on the deck and damage itself. And that's because they're landing them on the deck up off of Charleston, South Carolina, where the winter months have a little more toss and turvy ocean waves. So by launching the rocket and making it go east and then making a dogleg turn, they can have the first stage land on a landing vessel, unmanned landing vessel, autonomous, out in the Atlantic, just north of the Bahamas. So they're going to be launching another, I think it's, let's see how many it is. I think it's 46, no, 49. It's 49 satellites that they're going to launch. These are to fill in the North Pole and South Pole gaps. My guess is that Starlink is wanting to, or is actually selling the internet service to research projects that are near the North and South Pole. and they want high-speed internet access, and they can't get it from the geostationary satellites. So they'll go with Starlink. And Starlink, who would like to have Earth-wide coverage, we'll put a few more up there. And it's going to be around longer than most people think. The International Space Station funding has been approved through 2030. And there are already people saying, metal fatigue will take its toll by then. It'll be disastrous to be up there or hazardous to be up there. And if you remember all of the issues that the Russian Space Agency raised about, there's cracks. Well, it turns out all the cracks are in their modules, not in the other modules. And the leaks are also in their modules, not the other modules. So maybe Russia would want to replace some of those or patch them up, but the International Space Station is going to be in operation until 2030. I guess that's even if other organizations launch their own commercial space stations. And some of the other fish I was frying this week is trying to identify and then observe the Webb space telescope in the night sky. Now, given that it's unfurled or deployed its sun shield, it ought to be quite a bit brighter than when they first started taking pictures of it. It started out that you had to have a 17-inch reflector telescope to see it at all, and then it dropped down to a 12-inch, and that was still before it unfurled its sun shield. Now that the sun shield is out, it ought to be quite a bit brighter. It'll be tiny, but I'm going to guess that it's at least a magnitude 6 or brighter. But until somebody confirms that with actual observations, it's not going, not going to happen. The last 2 weeks, it's been a cloud fest outside my house, and I've been looking forward to seeing it. As Orion goes to the western part of the sky after the moon sets, and unfortunately the moon is moving to the east, so it's hanging in there longer. We may have to wait even longer to get the moon out of the way, so to speak. But it's up there. It's in the Heavens Above website. You can ask for coordinates. Now, if you look at multiple passes, the multiple passes will have a degree of inaccuracy to them because it's not an Earth orbiting satellite. So they get the Kepler elements, the 2-line elements, the TLEs, and then they make a calculation of a pass, and then the follow-on passes will be a little less and a little less accurate. So go with the first visible pass you can get after they update the orbital characteristics, and so see what you can see. But it's right now hanging out. If you know where Ophiuchus is, and you know these sort of arms that spread out towards the belt of Orion before you get over to Procyon, it's right in that area. So if it's got any brightness at all, you'll either be able to see it on a clear, dark sky, or maybe with binoculars. But if you know where it is, I'm going to guess that if you have at least a degree of field of view in your telescope, on a clear, dark night, you should be able to see it.
Monroe, do you know when they're going to start the beginning of the elliptical orbit around the Alphone?
I can give you that information. Let me switch over here. This is one of the websites that I go to, and it tells you what they're doing right now, how far the mirrors need to move from 0 millimeters to 12.5. But this actually gives you remember me several weeks ago identifying setting the identifier numbers for each one of the mirrors? This is where they come into play. How much have they moved? But if you go down to here, where you see explore deployments, click on that. If you go to the very next one, you have mirror segments complete. L2 insertion burn is at launch plus 29 days. I wish they would tell us how many days away from today it is. Yeah. Launch plus 29. Let's see, it went up on the 25th. 6 from that would be 23rd. So it sounds like about the 22nd, 23rd of this month is when it's going to do its L2 insertion burn. But also
basically about a month after launch.
Yes, but also remember, Also remember they have some latitude in that. So if they're adjusting the mirrors and it takes them a little longer, they have no problem pushing this out by a couple of days. So 29 days after launch, or about the 23rd of this month of January is really
That
good.
gets them to L2, right?
That gets them to the point where they want to fire the rocket to put them into L2. It's not actually going to be at L2. It is somewhat short of the distance the L2 point actually is. And then it will do a rocket burn that will essentially not shoot it out any further. It will bend it up. And as it bends it up, then it will use its momentum wheels to curve that. And then when it gets at the far end, it will use the little flap panel, the trim adjustment, to have the solar radiation push it back. And then it'll use the rocket to go around again. So it's not a sustaining orbit as a precisely at L2 would be. It's an elliptical orbit. But this is not the first time that spacecraft have elliptically orbited L2. There's three actually, I think now there's only two. Gaia and Spectre are currently in L2 orbits. Herschel was in an L2 orbit, but I think they're moving it out into a sun-synchronous orbit now. But Gaia and Spectre are both in elliptical orbits that are smaller ellipses, and they're more vertical. Whereas the Webb is going to be a much larger, almost the diameter of the sun is going to be the width of the ellipse and tilted outward by about 15 degrees. What you can see is slowed down considerably. At one point, it was pretty much 1 mile per second, and now it's a little more than 1/10 of a mile per second. Is how fast it's going. Okay, and that's all the news that I have. Does anybody else have any news to report that I missed?
The asteroid, remember?
Oh, I commented on that asteroid. If you go to your Facebook page, I put up a comment there. Here, let's briefly talk about the asteroid that wasn't. Huge asteroid will pass Earth safely on January 18th. Well, you call it huge like you're going to scare us, and then you say it will pass safely. I know this is just you picking up the Earth Sky, but Earth Sky, in order to keep eyeballs on its website, has to come up with something that is fear, uncertainty, and doubt. Or it's an extinction level event. Otherwise, people aren't going to look at their website. So my response is, if you find a near Earth object that is coming out of the direction of the sun, and it is less than 2 days away from Earth, and it is expected to pass lower than geostationary orbiting satellites, then I'll drop what I'm doing and crack out my trajectory calculation tools and see if I should worry about what's going to happen next week. But this one's going to pass farther away than the moon. So there's more than a 300,000 mile safety margin on this thing. So that's another asteroid that wasn't. But the other one that I commented on was this one. How do we spot near Earth objects? It's basically with a lot of public participation and going, everybody calculate it. And it may be an amateur that sees it first and says, I think I've got something here. And there's a website you can go to. There's a Minor Planet Center website you can go to and say, I think I found something. And they'll respond back within a day and say, we already got that one cataloged, thanks anyway. Or they'll go, oh, I think we might have found another one. Here's the initial predictive track. All the amateurs go out there and look for it so we can get data points and calculate its true trajectory. And then they'll come back a few more days later and go, well, we've got 5 more observations, and turns out it's not even going to get anywhere near the Earth, and it may be a comet that's going to hit the sun. So,
Do you see the movie called Keep Looking Up?
yes, I did. Don't
look up.
Don't look up. Yeah.
Don't look up. That was DiCaprio created that movie so that people would stop complaining about climate change. So if he complains about something's going to hit the Earth, but all of the way in which governments and the public respond is the same as climate change. That's that movie. So if you watch it, I think it's an interesting watch. You know, if you watch the movie Gravity and didn't question any of the physics or whether it's reality or not, then watch Look Up and, you know, same sort of thing. Don't question some of the posturing that they're taking and just enjoy the movie. I think it's an enjoyable movie. Okay, tonight's presentation is going to be access and use of scientific research data. Next week's presentation is going to be back more tightly into the realm of astronomy. And that I found something interesting this week that pulsars, which are rapidly rotating neutron stars, are being used for gravity wave detection. LIGO and Virgo, the popular gravity wave detectors, have some shortcomings. They cannot get the very much different wavelength gravity waves. And so if you think back, there was an episode of Star Trek: The Next Generation where they created a tachyon net that they could measure cloaked ships passing through. So what you couldn't see but had mass would distort the timing of the pulses from the network. And that's what pulsar timing arrays are, is if you measure the time of arrival at Earth of a handful of pulsars in all different directions, and you measure them down to the nearest billionths of a second, and all of a sudden they get distorted by a little bit, and then they go back to their normal amount. That's because a gravity wave passed through the line of transmission from the pulsar to the Earth. And if you determine that over a couple of pulsars, you can actually watch the movement of the gravity wave across the galaxy. And they've concluded that this is real science. You can actually do this. But what's even more interesting, and this is a postulation at this point, they don't have conclusive data. They have some preliminary data. Much like there is a cosmic background radiation that's always there, and you can measure it all the time. Apparently, gravity waves at certain wavelengths are there all the time. There is enough things going on in the galaxy in the form of large energy bursts or movement of very heavy things like black holes, or collisions or mergers of things like black holes, that there's always some kind of ripple of gravity wave swarming across the galaxy. So it'll be interesting to see if they come up with a gravity wave map similar to the cosmic background radiation mapping. So we'll talk about that one next week. So a lot of people just wait for NASA or ESA or European Southern Observatory or other place to publish a announcement. Hey, look what we found out. Look what we've confirmed. But they don't give you the data so you can make your own discoveries. And that is a trend that's changing. So people that get interested in the raw data, or at least the vetted for quality data, are starting to gain access to this. You'll see this in amateur research programs or in citizen science programs. So these either ground-based or space-based research activities result in lots of data. And if the mission for the instrument is for a certain thing, that doesn't mean that they aren't also collecting data for other purposes that they may not even think of until the future. So if citizens paid for the data to be collected through a grant or government access, then the public should have access to the vetted data at no cost for their own personal investigations. And you shouldn't have to work for a NASA or a Canadian Space Agency or a European Space Agency in order to gain access to this data. And you should not have to request a research grant or a formal research commitment to have access to the data. And if you're self-taught or self-learned of certain scientific precepts, you don't need a college degree or a PhD. What you do need is self-motivation and a willingness to learn what it takes to get access to the data in order to do your what if. So if you're curious, and if you find that there's publicly accessible data and you learn how to access it, maybe you have to download it, maybe you have to do online queries, and then you learn what the data means, you can do your own data mining. But unlike a research scientist, you have no requirement to publish or perish. You can look at the data and go, well, I was thinking about, what about these values? Does that mean anything? And if you don't find out anything, it's, you had enjoyment looking at the data. If you do find out something that's interesting, there are places where you can go, ask an astrophysicist, ask a cosmologist, and you can suggest, hey, I think I might have found something here. But if you go that route, what they're going to do is, if what you ask is interesting, they're going to go start their own research activity, and you might get left out of the loop. But if you happen to have, let's say, I don't know, a YouTube channel or a Facebook page or something, and you post what you're doing there after you find what you think of as conclusive results, then you go listen to what your public audience, your commenters provide. And if somebody with a scientific background looks at it and goes, I think you may be onto something, great. But there's no way they can steal your thunder, because your thunder was there on the internet for the public to record, such that if later on, hey, here's somebody that has a Nobel Prize for having found out the same thing you found out. You can go back and point out, see this page, see this YouTube video? Yeah. So
The other cool thing about this is that some countries where they don't have very much of money to do those databases and research or anything, that open up for, other countries that are not like USA, Canada, or the countries in Europe, and they don't have that money for research. So you can actually have access to some data. So even the schools of physics and astronomy can use that data to publish papers and be an academic, even though they don't have the money or the resources to actually do that.
Yeah, and when you publish, you do not have to publish in a prestigious journal, which I found out if you want to publish in a prestigious journal, you may have to actually pay the journal to publish your scientific research conclusion, which is kind of like, well, what's the purpose of this prestigious journal? Don't you guys get enough money already from your, it being $460 a year for a copy of your journal, and you only publish 8 times a year. And you don't even publish in paper anymore. You only publish online. So how much is it really costing you, and why are you charging them? But yeah, the data is so large. If you think of it as how many different research programs do all these government agencies undertake? NASA has undertaken so many research projects, and now with their mandate to publish and to retain the data for historical purposes, even NASA gave up trying to have data centers to hold all this stuff. And if you remember back in the day, when the Apollo program was on the moon, they were recording their data on magnetic tape, and they reused some of the magnetic tape because NASA could not afford to buy new blank 9-track reels of tape, 1,200-foot reels of tape, which were around $20 a pop. So by storing them on like Microsoft or Google or Amazon-based cloud services, the data should be there as long as they keep paying the bill. And if they have a flat rate per year, it's going to be there for a while. Of course, if all of a sudden the likes of Microsoft or Google or Amazon have a catastrophic data center problem, all that data is going to be in jeopardy. So if, let's say, I don't know, the Yellowstone volcano goes off and takes out the upper west coast of the US and the central data centers, you may hope that the data centers in Texas survive. Otherwise, buy data.
I'm worried for if it's like a paid service is not belonging to the government, is that kind of data, those enterprise take ownership. So you publish your paper, but you don't own any of the of your work, because that data is stored and they take ownership. So I worry about that kind of ownership taken by enterprise when they do use the resources of the government. That happens a lot on the on the medicines and research, and they use the government financing to get the base research, and then they take ownership, and you end up paying royalties to the people who did not develop that thing.
It gets out further than that. Your taxpayer, your tax dollars paid for the data to be collected, but as soon as you publish it into a paper, into a prestigious journal, the journal owns the paper you published, and the public has no access to that paper and must pay for a copy of it. And you can either pay by the paper for a flat open access for a month, or you can pay an annual fee. Otherwise, you don't have access to research conclusions that are based upon taxpayer data. So I find that to be kind of interesting, but I've dealt with that in medical devices and medical device research where, hey, the US National Institutes of Health provided the research grant funding for the collection of that data, and then you put it in your research paper, and I no longer have access to it, but my tax dollars paid for it because it's in a journal that I'm not going to pay, $400+ a year for 8 copies, 8 monthly issues of it. So yeah, putting up paywalls for data that is paid for by taxpayers it's a little blatant in my book, but the government likes it because those prestigious universities pay campaign contributions, and the prestigious universities are the ones most likely to fund these scientific research journals. So yeah, it's left hand paying the right hand. So prior data answering new questions. As I was saying, if there's a research project with grant funding that has a specific purpose to answer a specific question, they may be gathering lots of data, and that data may only be meant to answer the question they originally postulated. But they may be gathering a lot more data than that could answer other questions, and the question may not come up until years after that project is already done, either concluded or produced as research work or whatever, but the data is just sitting there. So if the data is collected properly, in other words, it's fully defined data, and it's stored properly for a long period of time, it can be accessed much later by other than the original investigative team members to provide data that can probably answer new questions. And the way that citizen scientists have done this is they go back and look at sky survey images, looking for comets and asteroids and even exoplanets that were archived in the data, but that's not what they were looking for. So they never saw the data. They had what I refer to as scientific research blinders on. So all they're looking for is this, but they're actually gathering much broader data than that. So they never see it. And if they were to see it, they would make a little note somewhere and then go back and look at it later with a different set of eyes. The most noteworthy of this one was when we discovered pulsars. And if you look at the paper log, there's a little notation that says LGM. She was doing the observations for a different purpose, and she saw this recurring pulse on the paper log, and she wrote down LGM for little green men. And it turns out that was the first recorded observation of a pulsar. So come back later, you may find that the data you've already recorded is meaningful. And if you previously did it by manual or analog analysis means, you can now go back and have a computer analyze huge volumes of data for very small pieces of information. The data is not just pictures. There's also electromagnetic spectrum data. There's just raw, like bits, bytes, values, sensor data. So you can find information out in other things. For example, they found out that a stellar nova, a star going boom, actually was observable in radio at low frequencies before it was visible in the visual portion of the electromagnetic spectrum. But they didn't discover that until well after they were already looking at it visually. So you never know what's going to be there until you look at it. So we have modern tools for old inquiries. If you think back to when they first started finding asteroids and comets, they had what is known as a mechanical viewer that was a blink comparator. You put a glass plate, a glass photo plate here, and then you put tonight's glass photo plate here, and then you would look through what looked like binoculars, and there would be a flip plate that would allow you to see, I want to see the left image or the right image, and you would flip back and forth between them, and you would look for what the difference is, and you would go, oh, there's a little black dot that I didn't see the first time. And then you flip back and forth, and you would mark the plate as, I think there's something here. And then you would watch that dot move over multiple nights worth of plates. Well, you don't have to do that anymore. Nowadays, what they've done is they've digitized those plates, and you can have the computers scan through the archives and find things. And one of the things they're looking for right now is Planet 9. Mike Brown and his team are looking through old archives of scanned photographic glass plates to see if they see anything that the visual observing community, by looking through the mechanical blink comparator, missed. And they have found asteroids, but they haven't found Planet 9. So new software looking at old data, because it can data mine bulk data, may be a way of finding things they didn't even know were there when they originally looked. So new approaches to data management. The NASA plan for increasing access to the results of scientific research came out in December of 2014. This was basically Congress saying, hey, we're giving NASA lots of money to collect lots of data. Where's all this data going? And Congress said, NASA, you need to start archiving this stuff and making it publicly available, because it was taxpayer dollars that created this data in the first place. So NASA actually has software developers on staff that create open source software for analyzing the data. And they also create online documentation for the software interface, the how do I gain access to this data? What do the data values mean? How do I process the data? What are the units of measure of the individual data values? They've got documentation for doing this stuff. And you can actually go to NASA websites and use the NASA tools to look at existing NASA data, even if you're not part of a research project, which is like, that's a giant leap in the right direction. So how long is the data supposed to be out there, and how often does it get updated? Some missions, some satellites and such, they record only data for the duration of the mission. So for example, when a spacecraft that is doing monitoring of the sun runs out of fuel and can't sustain its orbit, it may plow into the sun as a means of not having that wayward satellite go somewhere wrong. So what is the data duration? Well, it's as long as it was recording until it could no longer record, and that data exists, and we've archived it, so it'll never be updated unless somebody makes notations or improvements or corrections to the data. That data may never be updated, but it's archived for future reference. Some data is infrequently updated. So if you're part of a long duration mission and you only upload data once every 30 days, like Kepler did, the Kepler spacecraft, it would gather and munge data, and then about every 30 days it would get close enough to Earth that it would spew out its guts of data, and then they would update the data archives on Earth. And when it stopped doing its observing, then they no longer had periodic updates. So there's no real assurance of a periodic update, but some data is updated quite often. For example, weather satellite data is updated every 4 to 8 hours, and all of that data is retained. So if you want data about the Earth, you may find that there's just more data than you ever thought you could have access to. Many, many terabytes of data per month. So you may be looking at current data, you may be looking at recent data, or you may be looking at archived long ago data. But all that data has meaning if you are looking for new things that they weren't thinking existed originally. So if you're not into data mining, if you want to have something go look it up for you, there are websites that will give you all the data pertinent to what you're looking for. So if you want to look up, for example, a galaxy and say, how far away is that galaxy? How big is that galaxy? How many stars are in that galaxy? NASA's already done all the legwork on that. And all you have to do is go to the NASA NEDS website. Sometimes it's called NEDS, and sometimes it's just called NED. But if you go to the NED website, you can just key in the search word. I want to go find out information about the galaxy NGC 2237. And when you do that, it will tell you all about it, and not just in visible light. You can find data and images because it'll link off to other websites where it stores infrared, ultraviolet, X-ray, gamma, radio data for this galaxy. So if you just want, instant gratification of, I want to find out about this. If you know the name of what you want to find out about, just enter it and have it go look it up for you. But you may have to look it up under different names. So if you said, I want to go look up, Messier number 11 or something, you're probably going to find it because that's a very popular catalog. But if you said, I want to go find Caldwell object number 49, that might not be a NEDS. You may have to go look at Simbad in France. Simbad in Strasbourg is another favorite website I have for looking up stuff. Its purpose is really to link you off to some of the data, but where it really shines is if your astronomy software doesn't know the name of what you're looking for. If you say, I'm looking for Caldwell 49, and your planetarium software says, I have no idea what you're talking about. Give me a catalog identifier that I know because it's built into the software. You go to Simbad, look it up as Caldwell 49, it'll find it, and then you look at the table at the bottom of the page, and it'll say, oh yeah, that's also known as NGC 2237. Now you can go back to NEDS or to your planetarium software and target NGC 2237, and now it can find it. So, plus these days you can also do a Google or a Wikipedia search for it and find out information about it. And then you can go do a NEDS or a Simbad if you want a lot more data than you ever thought you wanted. And here's the secret. Here's how I found out data from Sophia. So if you knew the mission flight numbers, for example, 155 and 156 of cycle 2, then you can go out into the archive, the Sophia archive, and look up information. And it will tell you, well, we were targeting this. The airplane had to be pointed in this direction. It was at this right ascension and declination. And here's all the raw data that we gathered. Here's the analytical conclusion data. And here's the data that went into that journal report that you have no access to, but you have access to the preliminary data from Sophia's own archive. So even if you can't, or you don't want to pay the $400 to access it from the scientific journal, you can at least go and get the raw data. But how did I know it was OC2B flights 3 and 4, which are flight operations 155 and 156? That was because I knew the date that the flights run. 2014 was the year, March 22nd through the 24th. And that way I could look it up. A lot of these sites have correlative data keys. So if you don't know it by what they want you to know it by, which is FO 155 and 156, but you know the date, you can look it up by date. And also it'll tell you the instrument they were using on board, like forecast. They left out the E. Okay, so NASA has, through JPL and through Caltech, a lot of websites where you can go become a citizen scientist. And they've pretty much concluded the data. So you don't have to do a lot of your own true research. It's already been concluded for you, and all you have to do is go look for it. So if you're looking for exoplanets, for example, there's already tools out there that can process the data that is there, and then you can go use one of these sites. So there's Exoplanet Watch, Exoplanet Explorers, Planet Hunters, which makes use of test data, which is where that citizen scientist found that Jupiter-like planet. If you want to go look for it says Planet 9, but it's Plan 9, right? If you want to go look for Planet 9, you can go through Backyard Worlds. All of these are accessed through the Exoplanets NASA.gov citizen science website. But it's not just NASA, it's Europe. So the European Union has the European Southern Observatory, which there's observatories in South America and in Africa that they fund to operate and create. And you can actually go to their website and look up which telescopes have access to what images. And one of the ones that's a survey telescope is the Very Large Telescope in Chile and South America. So you can go look up, stroll through the archives. And if you don't want to look at raw data, you want to look at the pretty pictures, they've got the pretty pictures there. And the VLT is facility number 62. That's why there's a 62 in the web link. There's no cost to access it. You can just go stroll through the images, enjoy what you want, download what you want. But if you want to make commercial use of the data, then they expect you to at least file that you are doing so. And remember that the European Southern Observatory does visual, infrared, and radio wavelength observing. They have a lovely telescope, multiple radio telescopes in South America. It's called ALMA, operates in the microwave region. At an altitude so high, you have to wear oxygen. And if you have young and budding astronomers, the Harvard University, in conjunction with NASA, hosts Micro Observatory. And that is a collection of 6-inch reflector telescopes that if you're a student, I guess it's in elementary or middle or high school, you can remotely operate these. They're located in Cambridge, Massachusetts, and Amado, Arizona. You go in there and it's kind of like an introduction into doing remote professional astronomy. You select a target, you select your exposure, your filters, maybe some other parameters. You tell it what email address and an observatory that you'd like to hopefully capture the image. And then they give you a link where you can download your image, and they'll send you an email saying your image is available. And they have a challenge that you can take your image and then submit it back to them, and they will do a photo challenge. So who has the best image taken by a micro observatory hosted by Harvard? It's kind of like PR feeding its own engine. But what if you're into looking down instead of looking up? NASA obviously has a lot of satellites orbiting the Earth, looking down for change. Sometimes it's change within 4 to 8 hours, like weather satellites. Sometimes it's infrared satellites looking to see how much a rainforest is being cut by on a once a month basis. Sometimes it's the U.S. Geological Survey. They're looking for how low the Colorado River is getting. So looking down, there is a website called earthdata.nasa.gov. This is an overarching site where you can go look for satellite originated data that's looking down instead of up. But what if you're an amateur astronomer and you want to find sources of light pollution? I've actually done this. I found that at Harold Campbell, there was a weird source of light not too far from Harold Campbell that seemed quite bright. So I went to the Night Lights site and I keyed in the latitude and longitude from Google Earth as to where this light source was. And then I found out what it was. And it turned out to be a South Florida Water Management District, I guess you could say, spotlight that was supposed to be on a building that due to wind and rainstorms actually got tilted upwards. So it wasn't doing the Water Management District any good because it wasn't pointing at the building anymore. And it was harming amateur astronomy because it was directly night sky glow that if you have a high humidity night, it contributed to the local light pollution. So I found out where it was, what it was. I sent the information off to the South Florida Water Management District, and they had a facilities technician go out there and adjust the light. Yay! So
How did you know its latitude and longitude?
Oh, well, I knew where Harold Campbell was, and I knew about where the light was, and then I went to Night Lights Worldview, keyed in that latitude and longitude, and I found the light. And when I found the light source, I could then use a more precise latitude and longitude that I could then go back to the county property appraiser for Hendry County and find out, oh yeah, that's water management owned property. And then I have my connections at Water Management District and I can say, I think you need to have a facilities guy go out there and adjust that light. And the response was basically, thank you. And then within like a month, the light was corrected. And what thanks did I get? None. But I know that I reduced light pollution at Harold Campbell by just a touch. And if you want to see what it looks like at a very wide field, this is an image from Earth at Night, night lights. And you can see that out in the middle of the Everglades, there seems to be little pinpoint sources of light. Those are actually small cities in Florida that are out in the middle of the Everglades with growing light pollution. And if you look right about here, you can see that there's a spot of light. That's where Chiefland is. So the previous dark nights of Chiefland star parties is on its way out because you can see that from space. So you want to see how bright Bimini is? Here's Bimini in the Bahamas chain. That bright blob right there. So you can spot individual things. And when you zoom up, you can throw a grid over it and it will give you latitude and longitude. Major cities like, here's Atlanta. And there's Jacksonville. I mean, you can just spot the cities. Looky, Orlando. And then Southeast Florida just becomes a big white blob. So if you're looking for individual lights, you can probably find some out here. But once you get into the blob, finding individual lights is kind of a, you're not going to get the whole city to get dimmer. And if you want to get like as close to tonight's view as possible, this is World at Night Worldview. And you can start with historical data and then you can work to, for example, this is historical data starting back to January 1st of 2016. But you can look in a different layer and find like data from January of 2022 if you wanted to. And then, of course, you can use the zoom in capability and find where individual sources of light. See these 3 dots? What do you think those 3 dots are? Mile marker 35 on I-75, the rest area.
Oh,
Mile marker,
okay.
mile
Yeah,
marker,
yes.
Mile marker 63. No, mile marker 63 is over here. This is Snake Road, Government Road. This is the Miccosukee gas station. As seen from space. Precisely, dot, dot, dot. And that
Don't they
takes
have,
over-
don't they have like an airport for practice landings and takeoffs out there in the Everglades somewhere?
There was the old airfield that got decommissioned. There's no lights on that anymore. There are a number of small airfields out in the midst of the Everglades. Here is the Miccosukee gas station, but if you go up this way and follow Snake Road, that is the Seminole Indian Reservation. And then if you say, well, I'll go farther north where it's really darker skies, and then you see this little blob right here, that's that rural area that everybody likes to go buy land in because it's dark out there. It's not that dark anymore. Here's Clewiston. There's Clewiston, Florida. So, you know, once you know where all the cities are in a regular map, you can find where all these little light pollution sources are. So if, like me, for, you know, almost 20 years, I was always looking for dark sites out in the Everglades. I use these tools all the time to find where the lights are and be where the lights aren't. So what's missing? What's missing is I want to see what it was like yesterday, and I want to see survey images. So if you said, was the Webb telescope visible last night at all? Where would I go to find a snapshot of the night sky that I could zoom into that part of the sky and see it? Now, if somebody took a picture of the Orion constellation or the Ophiuchus constellation last night, if I could find that, I might be able to look for that data. But that's the one thing that's missing is very repetitive. I mean, they do this for weather, you know, every 4 hours, every 8 hours, they're going to survey the entire planet. Well, they need to start doing that on a looking up basis so that if you want to go look for something and you say, was that there last night? I don't know. There's no place where you can say, I want to go see the last thing that you captured last night from this location. Apparently that, you know, because there's no scientific research project or funded survey project to make sure that's done on a regular basis like they do for weather. It doesn't exist as far as I can tell. But if somebody out there finds it and says, yeah, I do this all the time. I wanted to see what the sky looked like last night. And there's this survey I can zoom around and, you know, Microsoft had this thing called Microsoft Telescope that you used to be able to do that, but it's not kept up to date anymore. It's kind of like fancy form of planetarium software. And every day that we don't realize that data is needed and we don't collect it for historical retrospective analysis is another day that information is lost. Okay, in conclusion, if you have the motivation and time, you can do your own research, get the data, vet it, peer review it. It's there. There are many starting points. Some of them are mission purpose or university related. There are granted research efforts that collect petabytes of data per day and use it for narrowed research, authorized research. But due to government mandates, that is becoming more and more available to the public. They just make sure that it's actually valid data. In other words, was the sensor working correctly? Otherwise, they mark the data as not valid. But what the data means is a different story. And it's not just deep space stuff. It's also airborne and orbital instruments. So you can go look up Sophia data for as long as she lives. You can look up orbital instruments looking down at the Earth. So if you come up with new questions, you may be able to answer it from data that's already captured. Just have to access it. And if you do access the data and you might have discovered something, you can either drop that off at your nearest, you know, ask a cosmologist or something. and they may make use of your data and you don't get any credit for it because you didn't capture the data, you just analyzed it. You were just an analyst. You weren't actually the observer. You weren't the principal scientist. But if you publish it yourself through a web page, Facebook, or YouTube, then you can go back and claim you have some noteworthy usefulness of having, you took the data that they didn't find this in, you found it, and then they concluded, yep, you found something. So they'll do the peer review. If it's meaningful, they'll do the peer review whether you need to or not. And I provided a bunch of links as usual to all the various things.
Can you post the same links on the tab under the video on YouTube? Because that makes easier for the people to
Yes,
actually.
when I post-process the video, I have to remember to do that because I've been negligent in not doing that. Okay, any other comments or questions about roll your own science?
You should make like a intro for the video, like narrating, like in the first slide, just to tell people, this is a video for this, and if universities want to do that, you can get the data for your own research. You don't have to be at NASA to do that. So that's really good for all the schools. So do some kind of intro,
Yep.
and then if
And
you
make sure
need,
make sure it's not longer than 5 minutes.
yeah. So it's like in the first slide, you can narrate something, and then the other thing is that I don't know how the settings on YouTube, but you should allow Spanish legend for the video, for the explanation, because when I went to Colombia, I met a lot of people who were actually studying that, and then they don't have access to the stuff, the material, and it's very expensive. So that would be awesome, because there is a lot of, it's not just physics, astronomy, that is all the areas of science that they are asking questions, and that would be awesome to actually explain to them that here's where you can get your data and you can do your research and you publish your paper. That would be awesome. Like if you allow for Portuguese and allow for Spanish, because I might be able to, pass the video around. That's useful resource. That's really useful.
I'll look at that on our YouTube site, but I think if I came across that when I was setting it up and it said, do you want to allow closed caption in other languages? I would have said yes, because it's automated captioning. I don't have to, go do it. I don't have to enlist your services to do it every time I post a video. They do it automatically.
Yeah. Oh, the other thing is that if you have the how you call it when you have the text of whatever you're saying in English, if
Closed
you have
captioning.
the script, no, the script of
Oh,
the
the
video.
script?
No.
You're looking at the script. This is the script.
No, not the script. No, like every word that we say, you can have that text. I don't know how you call it, that one.
Oh, I don't use the Zoom capability for that because I found that it's not close enough to 100% accurate.
No, I don't mean the Zoom. I mean when you post on Facebook and you see the caption in English, you can find a way.
That's enabled, but you have to do it in your browser or in your YouTube app. You have to say you want the caption, you want the closed captioning to appear. I don't do anything on my end. I just allow it.
If you find a way to actually capture that, dialogue, everything, we might be able to translate that and then do a capture for a caption for the language.
I'll look into it on YouTube, but I think that they will automatically generate the closed captioning. They have their own service that does that. And if you do, then based upon what language you've chosen for the user interface, it will automatically produce the closed captioning in other languages. But I'll take a look at that because those are all valuable things in my perspective. Now, if I could just get them to do the closed captioning for the metric to SAE conversions for all the Americans.
Well, that one, like if you can understand the text and stuff, it's good enough. If you make a note of whatever numbers and then you do your own conversion. This database that you post here is very, very useful for places where you don't have resources, you don't have money for research. And this is really good because some teachers, they are very creative, they try to do stuff, but they don't have the resources. And sometimes, like, if they have to read, like, how many books or database you have to read to actually get this data. So now you organize the data is easier if we spill out and show everyone that easily. It's pretty good database.
Yes, I want to grow the value of our YouTube site and allowing people to adjust the presentation interface to include things like other languages or closed captioning text. I think that's great. I've made a note of those things. The next time I post, I will try and bump it up a notch, and I will put these links into the caption.
And then I can spill out for the people who follow me on Facebook that's going to be, very nice. Especially, I contact the teachers. I have some contacts that teach math, and I have some contacts that teach physics and astronomy. So that will be very, very useful.
Well, I have a question.
Sure.
About this an asteroid. Should we talk now about it or later on?
Oh, sure. You can talk about it now. Is this one that's going to come by and it's out beyond the moon?
Yes, but my question is, it says in July it will be back again. So now how is that possible? How is the orbit of that one?
Yes, that's called a near Earth object, and that is an asteroid that is probably orbiting out to Mars and back. So it's in a orbit that goes around Mars, or it's in a sun orbit. It's a what do they call those? Not Trojans. I think they call them centaurs. They've got a name for these things. It's a sun orbiting, repeating or recurring near Earth object. So it comes by every so often.
Well, it comes in July again, and then it won't do it for another 100 years or so. That's really weird.
No. What that usually is indicative of is when it comes by the Earth, even though it doesn't hit the Earth's gravity alters its orbit.
Yeah.
Mauro, I actually looked it up. It's just a simple, highly elliptical orbit. It's very eccentric orbit.
Yeah.
So, Manuela, it's basic something like this. So, when it's coming now, it's going this way, right?
Right.
And then goes around the sun and comes back in July, and then it's gonna be like near the Kuiper Belt,
Very far away. Yeah.
like
Yeah.
coming out of the paper kind of thing. So
it's
sun, Earth,
you know,
and then
But it comes back in July, and then it will be gone for a long time.
Yes.
So it's much like comets.
This. So it's basically doing this. So it's going. So it's now, and then goes and.
So
See you later,
it's much like comets. We see them
Yeah,
first
it's
on
like
their
a
way
comet
in.
orbit.
So as they're approaching the sun from deep space, they go by Earth, they go around the backside of the sun, and then they whip back the other direction, and they're going by us on the other side. This is why when you go to observe a comet or an asteroid, as it's heading towards the sun, we go out in the early morning and see it. But on its way back, we go out in the early evening to see it because it's on the other side of the Earth. So that's why they do that.
But this one is moving very slowly because normally they zip up in less than a month.
Yeah.
This is moving. It's very massive and it's moving very slowly.
Yeah, it's about a kilometer across. It's quite a not
It's
good
a
to
biggie.
receive.
It's a biggie. It's a biggie.
Well,
When it was discovered a few years ago,
Yes.
People were afraid that would be something dangerous because it was very big and it's coming close to us. But as they did the preliminary calculations of the orbit and get a little bit more data, they figure out, no, it's not that dangerous.
Yeah.
Okay. Remember, the Earth is going around the sun, and these Kuiper belt or Oort objects have very elongated orbits.
Mhm.
And as they come by, they may be millions of miles from the Earth, but
Sure.
we can see them. But the ones that are a million or less miles from us have a very tilted orbit. So they may get close to us, but on their way back, they're very far from us. So, everything in space travels its own trajectories, its own speeds, and there are things going by the Earth's orbit all the time.
Sure.
Only sometimes are they going by the orbit of the Earth when the Earth is within its ellipse, within that object's ellipse. You can have objects that are coming in from the Kuiper belt that make an ellipse around the sun, and the Earth is on the far side of its orbit at the time, and it's nowhere near us. Do we ever hear about those? No,
No.
because the media can't feed you fear, uncertainty, and doubt about it. It's
Well, I hear
huge.
sometimes because I follow the solar observatory. So sometimes we see little comments that they go like, oh, this comment is going to collide to the sun. But then when it gets close enough, it actually zips up and actually survives. So there are a few interesting data that they show,
Oh,
like some comments
sure.
going across.
They're called sun grazers.
Grazers, yeah.
A comet can get, well, relatively speaking, fairly close to the sun. They get closer than the Parker space probe does to the sun, but hopefully they don't have any electronics on board. But they whip around the sun, and if they're off just a little bit because they came too close to the Earth or Mars or even Jupiter, then their velocity is not sufficient on that orbit, and they crash into the sun because they just didn't have enough speed to make it around
Well,
this
the
time.
angle gets captured by the sun. So depending on the angle that it gets.
The ones that get captured by the sun are the ones we probably need to be more worried about because they're now in a much shorter, almost circular orbit. So we're going to see them more often. And a lot of the meteor showers are from comets that are recurring. So those are
Or asteroids too.
asteroids too, but those are close enough to us that they only get out around the asteroid belt or Mars or maybe Jupiter. They don't go all the way back out to the Kuiper belt of the Oort cloud. So those are repeaters.
But then the other thing, Manuel, about your comment is, or your asteroid, is that if it's crumbly, if it has a lot of matter that's going to fall off as it comes close to the sun, we might have a new meteor shower for a few years.
That's interesting.
Yes,
Yeah.
it'll leave its junk in our orbit. Thank you very much. Now we got to go plow through it.
So maybe next year we won't see the comet about the same time of the year, but we might have a new meteor shower.
Yeah.
Mhm. Yeah.
I'm assuming that the reduction in speed of the Earth orbiting the sun due to impacts with meteor showers is negligible.
Yeah, it is.
I just presume it is. I don't know that it is. I have never measured it. I don't remember having seen a NASA study on it. I'm just going to, for sleeping well at night, presume that it doesn't affect the orbital speed of the Earth.
Well, I read somewhere else that they're using laser beams to correct the trajectory of some space rocks.
Yeah,
Just
so yeah, they're
keep them
gonna do
out.
one that's like a proof of concept.
Oh,
So
yeah.
they're gonna have one mission that is gonna collide with an asteroid
That's
and
dark.
see how much of the trajectory is changed. And the other hypothesis, I don't know if that is a mission already, the one that's gonna do the laser and see if the gas coming out is gonna change a little bit of the
Yeah, the laser
trajectory.
seems to be effective, but how much?
Yes.
Well,
Yeah.
So it's now what they are doing is get the safe ones that are not too far away from Earth, but
Yeah.
are not in a collision trajectory, and they're gonna start to use proof of concept. There are a few ideas. One is collision, the other one is lasers, and the other one is just making one asteroid be orbited by a heavy spacecraft, and that heavy spacecraft is going to affect a little bit of the gravity and is going to change the trajectory.
nudge it
And
slightly here.
Yeah.
much,
Yeah.
because all you have to do is change a little bit the angle.
Right.
It's not necessary to totally change the trajectory, as long as it's far enough from Earth, like even less than a moon orbit, even though those are grazers, Earth grazers. It's safe enough not to collide with us, so we don't have to change. Now you have to, the other thing is that the more precise our surveys are, the more data we have about the orbit of those objects. And then we are mapping them years before they come near Earth. So we have time to actually launch a spacecraft to actually change the orbit. So all you have to do is a tiny little push, because you have to remember that when you do talk about angles, one little push close by multiplies the angle.
Widens the angle, sure.
It's not necessary to move too much. It's only a tiny little bit if it's far enough. If it's too close to count, like the movie, then you need, a big collision.
Well, like I said, if it's coming in from the sun where we just spotted it at the last minute and it's 2 days before it interacts with the Earth, I'll definitely do my calculations. But if we know about it months in advance and it's not going to get any closer than 3 times the distance to the moon, it's like,
Yeah.
But it does bother. It does bother.
It's the don't look up kind of thing. Yeah.
It does bother me just slightly that they can postulate that firing a 100 kilowatt laser will adjust the orbital characteristics of an asteroid, but they don't
It's not
connect.
the laser. It's the gas coming out. It's just the gas coming out that's going to change the trajectory.
In the vacuum of space.
Yes, you have push coming out, so that would work like how you call it in the spacecraft, the little gas that comes to adjust the trajectory.
Reaction control system, the RCS jet.
No, you call it, that is a little name like for jets. No, it's not jet. It's
Thrusters.
So yeah.
Those are called reaction control systems.
Yes, so
Yeah.
that's the idea, that using a laser to have gas coming out, and that would work like a thruster and change just a little bit. Those are solutions that work when the comet or the asteroid is far away.
Yes.
If it's too close, it's harder to change.
When I have gas coming out, it thrusts away the people that I'm near.
Yes.
Don't light a match. Don't light a match.
Well, when you see me shocking and then you silence, it means that I'm trusting some spacecraft too.
Yes. Or if you remember the second Aliens, movie, when the power plant was going to explode, and the way they knew the power plant was going to explode is it was having explosive venting is what they called it. And they showed you this distant view of this reactor building, and it just goes explosive venting. So that's what I refer to it as. Is I'm having bouts of explosive venting.
Yes.
Well, correction by head-on collision would be a bad idea, because that would make it worse than really we have a rain of stuff.
Yeah.
Yes. That's what a lot of people don't understand, because they did that with some movies. So they produced doing that, and people think, oh, that's the solution. But they don't understand that you put it out a lot of pieces now. Instead for you to have a loss of one city, you're gonna lose the whole planet.
No. What we need to do
everywhere.
is nuke it. We need to nuke it. Let's send Bruce Willis up to nuke it.
Sure.
Yeah, so
Yeah,
people don't understand that that's not the solution.
Well,
The
they don't
solution is a
understand.
discrete solution, a little bump, a little
Yeah.
collision, a little bit of laser, or a little bit of gravity far away and off that makes just a tiny little angle change that's
Mhm.
going to multiply, because now you're going to have, as it goes, that tiny little angle that is very close, now as it comes with the time is going to be wider and wider, and that's the easier way, but we need to keep up with all the surveys and
Yep.
put money in science to not just for the capturing the data, but putting money on science, but to have eyeballs looking at the data.
Well,
I think
careful
it-
who gets the money to do this stuff.
Yeah, I think it still holds true that there are more people that are employed at an average McDonald's restaurant for all the shifts. There's more people employed at a McDonald's than there are professional astronomers dedicated and funded to look for near Earth objects.
Right.
Because even NASA, when you go to their planetary defense website, they are desperately looking for amateurs to submit information, submit their pictures to the research, because they just don't have enough telescope time around the whole of the Earth to do that. And
Yeah.
you can't look for asteroids and comets in the daytime.
No.
Have to look at night. And North America is in darkness. Good, we can look at it. North America is in daylight. Well, what if it comes in from the sun? You're not going to see it. So, yeah. Okay.
That was a good discussion.
Anything else before I cease recording?
So no, not really. It's just that one more idea that you can put in your data of ideas for it.
Yep.
Explain how to change the orbit of a comet or an asteroid to avoid the
Well,
comet asteroid Hubble address on it.
You remember when you were looking at that horizon data in the Excel spreadsheet, and you saw this scientific notation with like 11 decimal places? All you've got to do is knock off 3 or 4 decimal places on the right-hand end, which is not a lot of mass movement. And if you get that at least 2 years away from Earth and you make that small a change, it's not going to hit the Earth. But you have to have all the calculations to know in the first place, it's worth it to go out there to do that, because you can't just move all the comets and asteroids under the hopes that they're going to hit the Earth. You've got to move judiciously only the right ones.
And the other cool thing that you can add in a presentation like that is show how many of the surprise ones coming out like after the sun, and then we finally find it. Like how often that happens that we missed it.
At
And
least
finally
at least once a year, NASA will announce an asteroid went by.
Yeah.
And
And then
went,
all the other like the space, no, the ballistic sensors that you have in the ocean,
yes,
how many times they go like, oh, that is an atomic bomb being exploded somewhere in the middle of the world. Oh no, it was just a big asteroid that could destroy your city,
yeah.
fall in the
Well,
ocean, and nobody saw it.
the ones that they detect are from the sonic boom of the explosion of the asteroid impacting the Earth. But the ones that I think are really freaky are 2 days after it goes by, NASA announces an asteroid that is, 500 feet.
Those shades.
No, 500 feet, and it passed below geosynchronous altitude.
Whoa.
Yeah, those are freaky.
It came in from out of the sun. Nobody even saw it. And they were doing a survey on that side of the Earth at night, and they saw it and they went, oh, here's a new one. It's moving away. Okay, it's moving away. Let's backtrack where it was. And they find out
Surprise,
2 days,
surprise.
2 days ago, it was, 1,000 kilometers in orbit. Anybody see that?
No
Nope.
shades.
Yes, it
No.
was up high enough that it did not interact with the denser parts of the Earth's atmosphere for us to see
To
it
see
like
it,
a meteor.
To
And it just
glow.
like it zipped through. I'm waiting for the one that says, one just got by us and it took out a satellite.
Yeah. But
Ah.
the probability is very
It
small.
will happen. It will
Yeah.
happen eventually.
But
Just
It
that
will
would be
happen
fun.
eventually. It will happen eventually, but I'm thinking the odds of winning the lottery are greater.
Okay, and then
who knows?
yeah, and
Think
then
of
the other
Murphy's
thing is
Law.
to mention the ones that actually hit Earth every day, they fall in the ocean, because as you can see, it's like most
Yep.
of the planet is water, and so nobody sees what happens. And
Yeah.
then even when it happens on land, it's always in remote areas, like middle of
Thank
the
goodness.
Everest and stuff.
It's
You
somewhere
never
in the
see
middle of
that.
Saudi Arabia, so that's good.
Well,
Yeah, so-
also there are the
Siberia.
there are the Earth descending ones where they're on a very high inclination to the Earth's atmosphere. So they actually come in at lower speed and their terminal velocity is such that they don't produce a sonic boom, but they land in Siberia or an ocean or someplace. And we don't know how many of those there are because we don't detect them.
Thank God.
I mean, you go into a snowbank somewhere and you see, a 40-pound meteorite. And that's the first anybody noticed of it. Like, how did that get here? Well, it obviously came down through the Earth's atmosphere. It didn't explode. There was no fireworks show. It came in at such a steep angle that it slowed down at just the right speed. It got a little blackened, but never made a sonic boom. So it didn't drift down. It obviously fell down at a couple of 100 miles an hour, but it
Yeah.
was not your typical asteroid. But that's the ones where somebody says, an asteroid fell through my bedroom window and landed next to me in the bed. Yeah, that has happened. Or the
Yeah.
one where an asteroid hit the back of my car and went through the trunk lid and out the bottom of the car. I've
And
seen
I
pictures
think
of
the
that
guy
one.
sold the car, and it was like they sold the car and the meteorite together, and
Yes.
that was like a lot of money.
Yeah.
And it was a kind of old car, but they make a lot of money because that's a rare thing to happen.
Yeah.
Like it fell off on your car or in your garage.
Space is big, but there are a lot of heavy gravitational items out there like Earth, the moon. We're all very thankful for Jupiter's existence. It ate a lot of stuff on our behalf.
Yep.
Yeah.
But we have to be thinking to Saturn too, because if it wasn't for
Well,
Saturn
Saturn's farther
existence-
out. Yeah.
Yeah,
Saturn.
but if it wasn't for Saturn existence, Jupiter would have migrated towards to the sun.
Yes.
Right.
Yes.
Yeah.
But that was so long ago. Who remembers?
Yeah.
She does.
Well, she wasn't around back then. There's just science that says it happened.
Oh, wait a minute.
What?
I'm 4.6 billion years old.
Yeah,
Wow.
we are.
Yes, the elements that make you up are that old.
Yes,
What are you
sir, we
talking
are.
about? I'm that old. I'm 4.6 billion years old.
Yes.
I'm a little older than you, which is why I have the grayer hair. So
Ah.
I'm 4.6.
13.7?
No, I'm
13.7?
I'm 4.6 ... 1.
Okay. Oh, I go like the jokes that people who don't know much about science go to work in a museum, and they go like, how old is this meteorite? They say this 4.6 in a month years old. I'm
Never
like,
mind.
how do you know that detail of date? Oh, no, it's being the time that I work here.
I'm
Like-
not much older than the meteorite.